Hey guys, so today and next class, so this is 2 lessons, I'm breaking this up into, we're going to graph rational functions. Okay, we're actually going to today look at the pieces of information, just like we did the features, and then next video you'll see that that's pulling all the features together to graph it. Okay. So when we say rational functions, we're talking about where we have a numerator and denominator. We have a function in the numerator and a function in the denominator. So our parent function for a rational is 1 over x, and this is what it looks like right down here. And what I want to point out when it comes to rational functions is that you might see that we have what's called a vertical asymptote. See how your graph never touches that line right there, that vertical asymptote. And in some cases, most cases, we have a horizontal asymptote. Okay, again, never touching those asymptotes. I'm going to show you how to find those today. So, vertical asymptotes. Where do they come from? Well, vertical asymptotes talk about the denominator, talks about what can't happen in the denominator, okay? Now, what I want you to keep in mind is for a vertical asymptote, we set the denominator equal to 0 and we solve. And then that is our vertical asymptotes. There are situations, which we will come into in the future, that we have holes in our graph. It's when you can cross something out. But the truth is, the vertical asymptote trumps the hole, right? There can't be a hole there if we can never get close to that point, which is on the asymptote, okay? Now, horizontal, I said most of the time there's a horizontal, but there's also what we call oblique. So I'm going to show you what this looks like. So as you can see for the vertical asymptote, which we talked about up here, the vertical asymptote can shift left or right. Okay, so in this picture here, we see that our vertical asymptote shifted to the right. Now, horizontal, of course, horizontal can shift up or down. And I'm going to show you how to figure out, hey, is it right on the x-axis or is it above or below it? And we're going to do that. Now, with rational functions, if you do not have a horizontal asymptote, you have what's called an oblique. This year, we're not going to actually solve for them. I'm just showing that they exist, and I'll show you how you know it's going to be an oblique one. But when you get up to your upper level math class and you'll have these, you will solve for these oblique asymptotes, okay? All right, let's change. All right, so here I want to take notes on how we find these certain things, okay, these features. So the first thing I want you to do, no matter what, even though this says step 1, technically that's not step 1. Your step 1 will always be to factor the numerator and denominator. That's going to help you out the best. Then what we want to do is identify the domain. The domain, what we need to think about is what's not allowed. So in rational functions, we have to think about what's not allowed to make it divide by 0. So in other words, what makes the denominator equal 0? And that can't happen in our domain. The X-Intercepts, okay? X-Intercept, we went over last class, we can get to by setting y equal to 0. Well, what does that mean? How do I get 0 when we have a rational function? Well, rational, you think of fractions, right? So when we have the value of 0, what we're actually looking at is 0 over any number, but 0, of course. So to find the x-intercepts, what we want to do is we want to set the numerator equal to 0, and then we solve. Equal to 0. And then we also reviewed last time, oops, there's the lunch bell. We also reviewed last time that to find the y-intercept, we just set all the x's equal to 0 and solve. Okay. Now, let's go over again, and this way all of our notes are together. Vertical asymptotes. The way to find the vertical asymptotes is we set the denominator equal to 0 and solve. Now I want to go over the fact that since the intercepts are a coordinate pair, they need to be x comma y, where the vertical asymptote is a line. So our answer is going to be in a x equals a number format. Holes, okay, once in a while this will come up. Not very often though. Holes come from where when you factor, things can cancel out. So I want you guys to keep in mind that this is about what crosses off. In a graph, what will happen with the hole is that you'll see something like, there it is, open, and that would be your hole. Does this always happen? Not really, but once in a while it does, and I'll show you where that comes from, okay? Now, this is the important part, the horizontal asymptote and the oblique. Now, a horizontal asymptote and the oblique asymptotes actually come from your leading term's exponent, okay? It's about the exponent. So we have three different cases. We have this case 1 where the numerator is a less than the denominator. So what does that mean? I'm going to show you an example. So if we had x squared over x cubed, you see how the 2 is a less than the 3. So in that case, anytime the numerator is less than the denominator, we have a horizontal asymptote at y equals 0. Okay. Case 2 is when the exponents are the same. So I'll give you an example. Let's do 2x squared all over 3x squared. When they're the same, what we do is we use the coefficients in front. So it's almost like I get rid of them and I look at the numbers there. Okay, so in this case, we would have a horizontal asymptote at y equals those coefficients in front, which is 2 over 3. Let's keep in mind that if I have x squared, that's the same as 1x squared. So when I talk about the coefficients in front, if it looks like this, it actually means 1 is in front. Okay. And the third case, finally, of course, if the numerator is less than here, numerator and denominator is equal here, that means my third case must be where the numerator is larger than the denominator. And this is where we have our oblique. For those of you who want to try it out ahead of time, you can see that to find the oblique, we do long division. But again, don't worry about it this year. Next year, you'll go through it. Now, I'm not going to go over step 4 and 5 right now because I said that's going to be for our next day, okay? So let's start going over some of these together. All right. So the first step we have here, remember, it's not so much the domain, but what do we have to do with all of our functions first? We have to factor them. So in the numerator, can we factor it? No, it's still x minus 1. But in our denominator, we can factor it. I'm not going to show you how to factor right now. I'm just going to factor on the side. If you're having trouble factoring, make sure you contact me and we talk about have a one-on-one lesson, okay? So when we factor, we get x minus 3 times x plus 2. Nothing cancels. By the way, I'm mentioning that because if it cancels, then there is a hole. So now when we talk about domain, and I'm going to talk about it in two different ways. I'm going to talk about it in what x cannot equal, and then put it in interval notation. So what we need to look is at the denominator. What can't x be? In other words, what makes the denominator equal 0? Well, in this case, x minus 3, what makes that equal 0? Well, that would be 3. So I know x can't be 3. And if I look here, what makes that 0? -2. So x can't be 3 or -2. Now I told you I was going to show you how to write it in interval notation. With a rational function, if you look at your first page, the domain of the parent function was -infinity to 0 and 0 to infinity, correct? So we're going to start with -infinity. But what we're going to do is go to the smallest x that it can't be, which is -2. And then what happens is that we continue very close to -2, so put -2 down, to the next one, which is 3. And then we go from 3 to infinity. This interval notation, because we are using parentheses, says that we get really, really close to -2, but we never reach it. We get really, really close to 3, but we don't reach it, okay? Now let's do our x-intercept. Do you remember how to get our x-intercept? If not, look at that second page of your notes right now. To get the x-intercept, we take the numerator, and we set it equal to 0, and we solve. Now remember, the x-intercept is a coordinate pair, so let's make sure we put it in the coordinate. X-intercept has our number, comma, 0. Y-intercept. Y-intercept is when we set all of our x's to 0, right? Because it's 0, common number. The great thing about the rational function, always look at the original function, and I'm just going to cover up all the x's because they equal 0, right? And what are we left over with? -1 over -6, which reduces to 1/6. Now, let's look at vertical asymptotes. Remember, vertical asymptotes are what can't happen in the denominator. Well, what can't happen in there? It can't equal 3, and it can't equal -2. Remember, those are lines, so we have to put x equal. Holes. Holes are what we crossed out. Did we cross out anything after we factored? No, we did not, so there's none. Now let's look at our horizontal asymptotes / oblique. So remember, I'm going to look at the leading term in the numerator and leading term in the denominator. So the leading term in the numerator is x to the first, and the leading term in the denominator is x squared. So which case are we looking at? If you look, we're looking at case 1, where the numerator is smaller than the denominator. And if you look at your notes, that means that there is a horizontal asymptote at y equals 0. What we're going to do right now is we're going to sketch everything on our graph for now of what we have. And then next time, we are actually going to scratch the whole graph. All right, so our x-intercept's at 1, 0. Our y-intercept is at 1/6. I'm just going to do that there. Let's see, we have a vertical asymptote at 3. So 1, 2, 3. And I'm going to do vertical asymptotes we usually mark off as a dotted line. Let's see, and at -2. And our horizontal asymptote is at y equals 0. Now I'm going to actually highlight this because there's another trick to it, which I'll explain when we graph next class. Okay? Awesome. Let's see if we can do the next one. Example number 2. All right. So what we're going to do with this now, remember the first thing we need to do is factor. So in the first one here, if I look, there is a 2 in common, so it's greatest common factor. But then I also noticed that we have a difference of squares now in the numerator and denominator. So I can factor this more. 2 times x plus 1 times x minus 1 and x plus 2 times x minus 2. Perfect. Let's talk about domain. Domain, what can't x be in the denominator? So x can't be -2 and 2. Let's put that in interval notation. Remember, start with negative infinity. Go to that lower value. Continue with that lower value and go to the next one if there is one. And then the last one to infinity. X-intercept. Well, X-intercept, we have a larger numerator this time. So if we look at 2 times x plus 1 times x minus 1 and set that equal to 0. This doesn't matter because if we divide both sides by 2, it's still 0. So what I'm really looking at is where is x plus 1 equals 0 and where does x minus 1 equals 0. So we get x equals -1 and x equals +1. 2x intercept. Is this possible? Yeah, it is. Do we have to have an x-intercept? No, we don't. But one of the things to think about is the y-intercept. Can the y-intercept be more than 1? No, because then it wouldn't be a function. Could there be no y-intercept? Totally. Okay, so here we have -1, 0, and 1, 0. Next, let's do our y-intercept. Remember the easy trick. Go to the original function, cover up your x's. We get -2 over -4. Reduce that to 1/2. Vertical asymptotes. Remember, that's what it can't be. Luckily for us, we wrote this down up here, so I know that we have a vertical asymptote at -2 and 2. Did we cross anything off for holes? Nope, we didn't cross anything off, so none. And what about our horizontal or oblique asymptotes? Well, what is the leading term in the numerator? It's 2x squared. What is the leading term in the bottom, or the denominator, right? X squared. They are the same, so what case is this? Case 2. Case 2 says when they are the same, we use the coefficients in front, which is 2 over 1. So we have a horizontal asymptote at 1/2. You want to sketch this like we did the other one? Help us out. All right, x and y intercepts. So x intercepts, we have 2 of them. Y-intercept is 1/2. Why did I put 1/2 here, guys? Did you see I made a mistake here? 2 over 1 is 2. I hope you guys caught that before I did. All right. Vertical asymptotes are at -2, dotted line, at 2, dotted line. And we have a horizontal asymptote at 2, y equals 2. So again, I'm going to do that with the highlighter. I'll explain later in the next video. And we're ready to graph, almost. All right, what I want you to notice before we even factor, remember I told you this year we're not going to do oblique asymptotes. How do I know it's oblique? Because the numerator is greater than the denominator. And if you look at that leading term, the numerator here is greater than the denominator, so this is an oblique asymptote. We would do long division to be able to find that asymptote, but this year we're not going to do it, okay? One more. Let's factor. So on top we have x minus 3. On the bottom we have the difference of squares, which is x minus 3 times x plus 3. Do you guys see what's happening? Can we cross off? Yes, we can. That's awesome. Now, I want you guys to be very careful at this because I have a lot of students who make this mistake. When we cross something up on top, does that mean the top is 0? No, it's not. What is it? It's 1. Okay. Now that we did that, so we know there's a hole in here when we get there. So what I want you to do next is we need to do the domain. So what can't x be? What I want to do is when you say x can't be, you want to do it before you cross off, for the fact that if you're crossing off, it's technically still there, but it's a hole, so it's not continuous there, so it can't be in the domain. So focus on this one. So x will not be able to be 3 or negative 3. So when we put that in interval notation, we have negative infinity. Now be careful because I wrote it in the different order here. So remember, negative infinity to the smallest one. And then we continue. So negative 3 to 3 and 3 to infinity. Okay, X-Intercept. This one, I like this one. This is a trick one, right? We take the numerator, which is in a reduced form, take the numerator, set it equal to 0. Wait a second. 1 can never equal 0. That can't happen. And since it can't happen, it must be that there are no x-intercepts. Y-intercept. Remember, y-intercept is when we cover up our x's. So let's cover up our x's because it's 0. So I get negative 3 over negative 9. If we reduce that, we get 1/3. All right, vertical asymptotes. Vertical asymptotes come from what it can't happen in the denominator. So what can't happen in the denominator? X cannot equal negative 3. This time we have a hole, right? A hole comes from what we crossed out. So here's what we do. We take what we crossed out, we set it equal to 0, and we solve. So that means we have a hole at 3. Now a hole is a coordinate pair. So what I have to do is plug 3 into the reduced form. So plug in to reduced form. When I plug 3 into the reduced form up here, I get 1/6. Horizontal asymptotes, let's see. The leading term in the numerator is x to the first. The leading term in the denominator is x squared. This is case 1, right? Where the numerator is smaller than the denominator. So y equals 0. Okay, let's just get it ready for next class. So no x-intercepts, The y-intercept is at 1/3. We have a vertical asymptote at -3, dotted line right there. And we have a hole. We have a hole at 3, 1/6. 1/6 should be lower than the intercept. Okay, make sure it's open. Open, that's what makes it a hole. And then we have our horizontal asymptote at 0. All right, you are ready to try this out on your own. 3 problems, should be 2, 4, and 6 on your homework.